So this topic is Demystifying SQLite with Python by Bhatia. She's an enthusiastic and passionate technology analyst at Goldman Sachs with 2.5 years of experience. Over the course of her career, she's evaluated multiple database systems with a primary focus on performance, durability, and scalability as per project requirements. She enjoys sharing her knowledge by simplifying complicated concepts and learning from fellow developers on her team. She loves learning new technologies and continually improving her skills as a developer. Ria received the Google Women in Technology Scholarship and the Nutanix Women in Tech Scholarship in recognition of her leadership abilities and contributions to the community. In her free time, she enjoys reading and playing music as a hobby. And I just want to also add, this is also a pre-recording. As I mentioned before, if you're having difficulty hearing the audio in person, you can also read and watch the captions in Fletcher Theater. So go out to the hallway on your right, or you can watch the YouTube stream on silent to read the captions. And we'll get started. Thank you.
Hi everyone. Thank you for coming and attending this talk. I'm Ria, and today we are going to talk about SQLite and Python. Firstly, I would like to thank the PyCascades team for giving me this wonderful opportunity. This is my first tech talk and I'm equally excited and nervous. Before we get to the main presentation, let me quickly introduce myself. I'm currently working as a software engineer in the fintech industry, and over the course of my career, I've worked with multiple database systems and evaluated different technologies. I actually worked with SQLite and Python back in college, and now that I understand databases better, I realize how cool SQLite actually is. I think what makes learning even more fun is diving deep and understanding the whys and hows behind all these things. Apart from my technical interests, I'm also very passionate about organizing outreach and mentorship initiatives for women in STEM and giving back to the community in whatever way possible. So, what to expect from today's talk? Firstly, we'll talk a lot about SQLite, its features, and what makes it so popular. We will deep dive and understand what is happening under the hood. How is data being managed internally with respect to storage and retrieval? Of course, we will see how we can use Python to interact with SQLite. And I hope by the end of this presentation, you are not just excited to use SQLite in your next Python application, but are equally enthusiastic to know more about other database systems. So let's get started. But wait, let's take a step back and get the basics right. What's a database? A database is a collection of records. On the most fundamental level, it should do two things. If you give it some data, it should store that data. And when you ask for that data again, it should give that data back to you. Simple. With this, let's also clear a common misconception. Most people think that the DBMS and the database are one of the same things. Well, the database is actually where your data is saved, while DBMS, that is the database management system, is a software program that manages this database and organizes that data in a certain way. So you could think of the DBMS as the brain of your database that is responsible for bringing order to the chaos. It's actually the DBMS which queries, creates, or modifies anything in the database and even provides the requested information back to the users. And this entire system together is called a database system. So all the popular databases you might have heard of like MySQL, Postgres, SQLite, RocksDB, Cassandra, all these are database management systems. Now is the time to talk about the star of our evening. But I have a question. Have you ever used SQLite before? Well, I wish I was there to see your reaction in person, but let me tell you that SQLite is one of the most widely used databases in the world. Apple uses SQLite in Mac OS and iOS to store calendar history, address information, and other applications. Google uses it in Android. Mozilla uses it in Firefox. And similarly, Cisco, Dropbox, Skype, Adobe, all these big companies are using SQLite in some way or the other. So, knowingly or unknowingly, you have used SQLite somewhere, sometime. But the question is, what makes it so popular? So, in very simple terms, SQLite is a public domain software package that provides us with a relational database management system. And it has the following features: it's open source, serverless, zero configuration, cross platform, small and lightweight, self contained. I know that's a lot of terms, but I can assure you that by the end of this presentation, you would understand all of them. Well, let's start with the easiest one. One thing to note here is that the light in SQLite nowhere refers to its capabilities in any way. Light, however, means lightweight when it comes to setup complexity or using minimum resources from the host machine, and providing an overall hassle free experience to both the developers and the users. But how is it different from traditional database systems? All the other RDBMSs you might know of, like MySQL or Postgres. Well, like other uh, RDBMSs like MySQL, Postgres, or SQLite doesn't follow a client server architecture. What that means is in a typical client server architecture, there's a large software package that actually makes up the DB engine. And in this DB engine, there are multiple processes which are working together and managing different things. So, say one process is managing file caching, another one is managing querying or connections, and all these are working together. So, a lot of inter process communication is happening. On the server's file system level, there are multiple files which are organized together in a directory structure, and the actual data actually persists in all these files. Since all these components require all the resources from the host machine, it's usually a good idea to dedicate a separate host machine to the entire database software package. And that is our server host. The vendor provides DB client libraries which are integrated within the user applications, whichever application wants to use the database. And these DB client libraries have APIs through which you can find and connect to your database server and talk to it using commands over the network. This is a typical client server architecture. What happens in SQLite is that there is no separate server. The entire database engine is integrated within the user application which wants to use the database. And all the information is stored in a single file on the file system. We'll talk more about this. But since there is no server, a lot of complexity is removed from the picture. So you can imagine that it becomes so simple, so easy to use SQLite as compared to client server architecture. And SQLite is mainly designed to address localized storage needs. By that I mean that it's perfect for applications which are lightweight and small, for or embedded applications like handset devices or cell phones, microwaves, television, where a typical client server architecture would be too complex or heavyweight. And SQLite is a perfect design for that. Talking about it being a relational database, so it stores user defined records in the form of large tables. And the DB engine is entirely capable of combining multiple tables depending upon your query and generating reports. SQLite is a single file DB. We discussed while discussing the architecture of SQLite that it stores all its data in a single file DB. Let's talk more about this. The entire database is packed into a single file. So the application using SQLite can open this database file like any other regular file and read and write to it using SQLite APIs. It's that simple. This database file is broken into pages of fixed size. It follows a page oriented architecture. And inside these pages are where our data resides, related to the tables or indexes or even the metadata. So you can see that each page holds certain number of rows of our table or of our indexes or whatever metadata we wish to save. Since there's just one file, it becomes so easy to create or copy or take backups of the database image. You could literally email this to your colleague just like a spreadsheet, and they have the entire database with them. So, again, it becomes really hassle free and really easy to use SQLite, and that is what actually makes it so popular. Now, when it comes to reading, even if you want to read just one data row, just one record from your table, you have to fetch the entire page, the page which contains that record, into memory. And this is called a disk IO or a disk read, and it's usually an expensive operation. Let's keep this concept in mind and we will get back to it when we discuss more about retrieval in future slides. For now, let's discuss about SQL, structured query language. So when it comes to relational database programming, you must know SQL. That is the only way to create, modify, or do anything with your relational database. So here is a quick refresher. These are the four type of commands which are there in the SQL world: DDL, DQL, DML, and DCL. Data definition language is all about creating the database objects like our tables, indexes, views, and they basically decide the structure or the schema of your table, of how your table would look like, what will happen, what will be inserted in this particular column, or how that table would be presented on a logical view. DML is data manipulation language. It deals with the records which are stored inside this table. So you could do that with insert, update, delete. You could do these operations on the records. Now, to fetch those records from the database, that is the reading operation, you use DQL, that is data query language, and that is done using the select query. DCL, that is data control language, provides accesses or controls to the users who can access the database or even revoke the control. Now, let's get to the fun part: SQLite and Python. Let me tell you, it's very, very easy to use SQLite with Python. The moment you install Python, you have the SQLite module with you, and you do not need to do anything separately. You do not have to install anything separately to talk to the SQLite database. All you got to do is install Python and you have everything you need. And that is why it's literally no setup when it comes to talking to or interacting with SQLite. Let's see how you can do that. So the moment you import SQLite 3 after installing Python, you have the module to talk to the database. The next step is to create a connection to the database. And of course, creating the database. Here, when the moment I write peopledb, people.db, if the database already existed before, it would connect to it. If not, if I'm doing it for the first time, it will create a database for me. So SQLite3.connect would create a connection to the database. Now, if you want to create an in-memory instance of the database, then you can use this command SQLite3.connect. It's an in-memory database, like all the data is in memory, as the name suggests. Now, in order to execute any SQL queries or fetch anything from the tables, or once we create them, we need a cursor object. It's a temporary database object which enables us to do that. The moment we create a cursor object using connection.cursor, we can use the execute function and create our table. This is a typical SQL statement for creating a table. Here is the name of my table, and you could see these are the various columns and they have a data type attached to them. Like what will be inserted, what value, what data type would be inserted in each of the columns. SQLite supports 5 types of data types, that is null, integer, real, text, blob. For this, I have used just integer and text. Feel free to create your own tables once this presentation is over, and experiment with all these data types. This is how my table would look like. This is the schema or the structure of my table. When I fired that SQL command in the previous slide, this is how I want my table to store data. The next step is to insert the records in the table. Again, you would use the execute function to do that. And this time you would use the DML command, that is the insert into the name of your table, and the values. These actually bind to whatever column they are supposed to go into. The insert here opens an implicit transaction which needs to be committed so that data could be saved in your database. And that is why after firing this query, we will commit the transaction. We will commit this statement. That means we want that this data to persist, to save in the database. We are telling the database, please save this data. Coming to reading of the records from the table, again, you would use the execute function and this time use the DQL, that is select query. And this star means that we are reading everything from our table. All the results are being stored in this result set. Once you do a fetch all on this result set, all the values would get printed. If you want just the first one, you could also use fetch one. Now, it's always a good idea to close your connection once your execution is done. With this information, you could literally do anything with your application. You could use different DQL, DML, or DCL commands, which are there, which we just discussed in previous slides, and create your application depending upon your needs. Now, here I've created a very simple application. And what I've done is I've inserted more than a million records into my database table. For this, I've used a CSV file, which I converted to a Python list. And then I use the execute many function instead of execute. And if you see that we have used question mark placeholders over here, which bind to each of the columns, and then we have passed the list. The difference between execute and execute many is that execute many does everything in batches, like it groups all the statements together and would send it together to the database rather than doing it one by one using the execute. Once this is done, again we commit it because it's a transaction. Then I'm timing my query. What I'm trying to do is I'm trying to fetch all the records of the people which satisfy this condition, that is they are greater than the age of 30, and then I want to order it in ascending order. Another thing which I've done here is explain query plan. Through this, I want to know what route did my database take to fetch this data. This will give me an answer of how did the database fetch my data from my file. Then I'm printing this query plan. Let's see this in action. How much time does it take to actually do this? Okay, so here is my application, and this is the exact same code which we just saw in our slides. And let's run it. I want to see how much time does it take to fetch all the records which satisfy this query. And we have the result. So it took around 3.88 seconds to fetch the results matching this condition, and the database scanned the entire table to fetch the records. Okay, so now imagine if we just have a million records right now and it took 3.88 seconds to fetch the records from there. Now, as our data grows, this table would also grow and this time would also increase, and at one point it will become so unfeasible for me to wait for so many seconds. So we need to optimize it, because in today's world, if your application is not fast enough, it doesn't matter how cool it is, right? So there has to be a way to optimize it. The obvious one is indexes. So let's create an index on our table, and we will create this index on this particular column, which is there in our condition on which we want to query. And this is the name of our index. Now let's see how much time does it take after creating an index, and also see what route did the database take this time to fetch all the records. Okay, so you see it took around 0.00, nearly 0 seconds to fetch all these records. And this time the database scanned the index to get the records, not the table. So what exactly happened behind the scenes which optimized the query so much? Let's understand that. So this is our table. This is how our table looks like on a logical level. We earlier discussed that all this data is stored into pages of fixed size in our file, and each page could hold a certain number of records. Now, the number of records a page can hold also depends upon the size of each record. So let's imagine hypothetical numbers that the size of each of the columns is given below: 4 bytes, 70 bytes, 70 bytes, 4 bytes, 12 bytes, and 40 bytes. And together, the entire row size is 200 bytes. Let's also assume that the size of our table is 600 bytes. So only three records could be stored in one page, that is 200 into 3, that is 600. So in order to hold 100 records, we need 34 pages. If you remember, we also discussed in previous slides that in order to read just one record, we have to fetch the entire page into memory. So, how would the retrieval happen? Steps to fetch a record. So, first we fetch the first page containing the table records into memory. We find all the records which match this condition. We store the results in a temporary buffer. Then we repeat all these steps for all the 34 pages because there is literally no other way you could find the record directly and then return the results. So if fetching one page takes 1 second, the total time here taken is 34 seconds. Again, this is just an assumption for explanation purpose. So 34 seconds we have to wait. If there was a way, if we could directly figure out the page number somehow, it would really make our job easier because we would directly fetch that page and get the record. Indexes would come to our rescue in this case. So let's create an index. By creating an index, I just mean that we will store a copy of that attribute separately. If you see, I've stored this in a sorted order. And with the copy, we are storing a pointer field. This pointer field is actually pointing or actually storing the information of the page number and the offset of where I'll find this record. Now let's see what will happen when we will query using an index. Firstly, this index would also be stored as a part of your database file in another page. And the size of your index is suppose 4 bytes and 4 bytes, 8 bytes. Now your database page size was 600 bytes. So one page could hold approx 75 records. So 100 records for 100 records, we would require 2 pages. So first we fetch the first page of the index into memory. We find the page number and offset of that record which matches this condition. Then we store the results in a temporary buffer. We fetch the next page into memory, find the page number and offset of the records which match this condition. And now finally, when we have all the page number and offset information, we can go and directly fetch those pages, those table record pages, and fetch the entire record and then return the results. So if fetching one page takes 1 second, total time taken here is 2 seconds and fetching actual record pages. That is again way less than 34 seconds. So we optimize the performance to a great deal using an index. Now the databases used a much more optimized approach. This was just done to explain how we would query using an index. We will discuss that optimized approach soon. What we saw here was an example of a secondary index. That age column was a secondary index. If you know that usually we create a primary key when we create a table. The purpose of that primary key is that the moment we create one, the database itself creates an index for itself. So you could imagine of using the employee ID as the primary key. So this is somehow the data is stored. Imagine all these boxes to be separate pages holding your data records. This is your actual data records and this is the index through which you can reach the records. Now as our table is growing, our index is also growing. Each time you update the table, you have to update your index as well. And at one point, again, as our table grows and as our index grows, it would become unfeasible to fetch so many index pages again into memory. It'll degrade the performance. So, how can we improve this? Let's create another level of index for our index pages. And this is called multi level indexing. This is exactly the idea behind B tree indexes. What happens in B tree indexes is that each node stores a minimum number of keys. It's a self-balancing tree which is height balanced. And suppose now we want to fetch the eighth record in using our B tree index. All we got to do is fetch the first page. It's in sorted order. Remember, we stored that in sorted order. We could run a simple binary search and find which would be the next page we should fetch. Fetching this would be useless for us because this contains data greater than 11. So we go to the next page, which is this. We again do the same things, run a binary search, and then we reached our desired page. This has our record, and within just 3 fetches, we were able to reach our desired record. That is why I earlier mentioned that the database uses a much efficient approach and you do not have to fetch all the index pages always into memory. What's happening in SQLite? So, irrespective of giving a primary key to your table or not, SQLite always attaches a row ID field with your entire table. So, each row already has a unique number a unique value, and this row ID actually is kind of a primary key for SQLite, and it stores the data in a B tree structure. For the index, for secondary index, here, rather than storing the pointer information, it actually stores the row ID. This is also an index on its own. The B tree index, there are two B trees. The table is also stored as a B tree structure. The index is also a B tree structure. So, in order to find, suppose, the person with the age 32, we first query the index. Then we go and find the actual record in our table, that is another B tree structure. With this, we come to an end of understanding storage and retrieval with respect to SQLite. Now, is SQLite perfect? No database is a one stop solution, it has its advantages and limitations. For SQLite, one disadvantage is limited concurrency. So it could support unlimited number of reader threads, but one writer thread, it locks the database file while doing that, which could cause performance degradation. And at that time, no other write could take place. Also has limited scalability. As we discussed earlier, that SQLite is mostly for application to cater localized storage needs, and it's great for application which have low concurrency needs or cannot handle very large amounts of data. For example, if there's a centralized server and multiple users want to connect to it and talk to it, then a client server architecture would be more suitable for such an application. SQLite's founder, D. Richard Hepp, says that they do not compete against any of the enterprise level databases like MySQL, Postgres, Oracle. Their competition is against F Open, and it's a way to re implement that in a more sophisticated and modern way. Thank you so much for attending this session. I hope it was useful in some way. If you have any questions, queries, or suggestions, feel free to get in touch with me. I would love to get some feedback in order to improve for my future presentations. Thank you so much again and hope you have a great evening ahead.